April 2025. A riverbank somewhere in northern Europe, just before dawn. Crates hit the ground, latches swing open, and 200 Eurasian beavers step out into a valley that has been biologically silent for half a century. No fish, no amphibians, no self-sustaining plant life. Officially declared a dead system since the mid-1970s. Then, on that April morning, the X-Force conservation team released their animals and held their breath. 200 individuals. That is not a large number. A single disease outbreak, one brutal winter, a contamination event nobody predicted. Any of those could have collapsed the entire effort before it started. Lead ecologist Alexei Volkov told his team to hope for erosion control, maybe some marginal water filtration. That was the realistic ceiling. That's not what happened. Within 18 months, salmon returned to a river that had not held a living fish in 50 years. Biodiversity measurements climbed 300%. The data came back and the team did not believe it at first. So what truly happens to a landscape when its lost engineers finally come home? I'm Dr. Henry Vale, field ecologist, and what you just watched is the opening chapter of one of the most improbable river recoveries on record. This is episode 4 of the series, and like every episode before it, we follow one complete comeback story from collapse to recovery, told through the data and through the people who lived every decision inside it. The X-Force project was built on a single conviction, that keystone species reintroduction, done at genuine scale, could do what decades of engineering and chemical remediation had failed to do. Alexei Volkov led the ecological strategy. Senior hydrologist Dr. Maria Ivanova managed everything the water itself was telling them. Together, they made calls that most of their peers considered reckless. What I want you to understand before we go any further is the weight of the starting point. A river with no fish, no amphibians, no functional plant community. 50 years of absence, 50 years of attempts to reverse it through conventional means, and 50 years of failure. The people who signed off on releasing those animals were not optimists chasing a headline. They were scientists who had exhausted every other option and were betting on something older and stranger than any technology they had access to. The full arc of how this river died, how every prior recovery effort fell apart, and what the beavers actually did to the hydrology and the soil and the food web. That is what the rest of this story is about. The answer is not simple. And some of it, even now, the models cannot fully explain. 100 years before the beavers arrived on the bank in wire crates and the cameras started rolling, this river was one of the most productive freshwater systems in the temperate world. Spring mornings along the valley, the water ran cold and clear over gravel beds the colour of old bone, and the surface broke constantly, not from wind, but from fish. Salmon pushing upstream in numbers that would seem impossible today, their bodies so dense in the shallows that you could hear the river before you could see it. A low, continuous churning, like something breathing. That is not poetic license. That is what the survey records from the early 20th century actually describe. The riparian forest came right to the water's edge on both banks, alder and willow leaning out over the current, their roots threading down through the bank and into the riverbed itself, holding everything in place. Behind the tree line, the ground was wet and spongy for 50, sometimes 100 metres back from the channel. Beaver ponds dotted the floodplain at irregular intervals, each one a small reservoir of still water behind a dam of sticks and mud, each one raising the local water table and feeding moisture slowly back into the surrounding soil. The whole system was, in the language ecologists use now, hydrologically coupled. The river, the floodplain, the forest, and the groundwater were not separate things. They were one thing, operating together. And then the 20th century arrived with its particular kind of ambition. Industrial expansion along the valley began in earnest through the 1920s. Mills, processing plants, and eventually larger manufacturing operations found the river useful in the way that rivers were always found useful in that era, as a drain. Effluent went in. The current carried it away. What could be simpler? By the 1930s, discharge from upstream operations was measurable in the water chemistry at points more than 30 kilometres downstream. The river was absorbing it for a time, the way a body absorbs small doses of something toxic, quietly, without obvious complaint, while the damage accumulates in the tissue. Channelization came next. The bends and oxbows that had always made the river inefficient for adjacent land use were straightened through the 1940s and into the 50s. Wetlands on the floodplain were drained for agriculture. The willows and alders along the bank were cleared to make the channel accessible and to open land for grazing right to the water's edge. Every one of those changes was rational in isolation. Every one of them was also severing a connection in the larger system that no one was accounting for. The beaver colonies, which had already been reduced by trapping pressure through the 19th century, disappeared entirely from the valley by the early 1950s. That detail would not seem important to most people at the time. It would come back to haunt the river. But that's getting ahead of the story. By the 1960s, the invertebrate surveys were coming back nearly empty. Invertebrates, the mayflies, the stoneflies, the caddisflies, the small crustaceans living in the gravel, are the base of the food web in a river system. They are what the juvenile fish eat. They are what tells you, before anything else does, whether a river is functioning. A healthy, temperate river should return hundreds of taxa per sample. The surveys from this stretch of water in the mid-1960s were returning counts in the single digits. That's the kind of number that makes accountants cry. It means the ledger is nearly empty. The salmon runs, which had already been declining through the 50s, effectively ceased by 1968. Not declined, ceased. The gravel beds where they had spawned for thousands of years were still there, technically, but they were silted over. The fine sediment that had once been trapped and filtered by wetland vegetation and beaver ponds now moving freely through the system, settling into every gap between the stones, suffocating whatever eggs might have been laid there, and then the official language caught up with the biological reality. In the mid-1970s, environmental monitoring bodies formally declared the river biologically dead. That phrase carries weight, but it is worth understanding precisely what it means, because it is not a metaphor. Biologically dead has a specific scientific definition. It means dissolved oxygen in the water column has fallen below 2 milligrams per litre. 2 milligrams. For context, a healthy river runs at 8 to 12 milligrams per litre. Salmon need at least 7 to survive. Most invertebrates require 5 or 6 just to persist. Below 2, almost nothing can live. The oxygen depletion was driven by the organic load in the effluent. Bacteria, decomposing the waste, consumed the oxygen faster than the water could replenish it. And the straightened, fast-moving channel that might have helped reoxygenate the water through turbulence had itself been degraded, its banks bare, its flow unimpeded, but also unstructured. The food web was not damaged. It was severed. Not frayed at the edges, cut completely through. There were no self-sustaining aquatic populations of any kind. Not remnant populations, not struggling populations, none. And then the engineers made the one decision that changed everything. They looked at what they had created and concluded that the solution was to clean it up. Which sounds right. Which sounds like exactly the correct response. Clean water in, problem solved. That logic would drive the next 50 years of effort, and it would prove to be profoundly, expensively, heartbreakingly incomplete. Everything was in place for recovery. The river just didn't know what everything was building toward. Picture the river in the summer of 1989, 14 years after the Dead Declaration. The effluent regulations have been in place for nearly a decade, and the water chemistry has measurably improved. Dissolved oxygen is creeping upward. A monitoring team wades into the shallows in the early morning, nets in hand, and pulls their first invertebrate samples of the season. They find something. Not much, but something, a scatter of tolerant species, the biological equivalent of pioneer plants on bare rock, organisms that can survive in conditions that would still kill most things. The team leader writes in the field notes that the river is, quote, showing signs of life. That note will be cited in 3 subsequent funding applications. It will anchor an optimism that the data, taken whole, does not quite support. The clean-up campaigns had begun in earnest by the late 1970s. Industrial discharge was regulated, then restricted further through the 1980s as legislation tightened. Sediment was dredged from the worst affected stretches of the channel. Native plants were manually replanted along sections of the bank, crews of volunteers and paid contractors pressing willow cuttings into the mud by hand, staking them against the current, returning in subsequent seasons to find that many had held. By the late 1980s, aerial photographs of certain sections of the river showed a thin green line re-establishing itself along the water's edge. Progress, clearly. Real progress. And then it would collapse. Not dramatically, not in a single event. It would just slowly, quietly fail to hold. The planted willows would establish, but without the root systems of a mature riparian forest, they could not stabilise the bank against flood events. A wet winter would scour them out. The invertebrate population that had begun to recover would spike in a good year and then crash when the conditions shifted. Fish were reintroduced on at least 4 separate occasions between 1981 and 2003, stocked directly into sections of the river that the monitoring data suggested were now viable. The clock was already ticking on each of those attempts. The fish just couldn't hear it yet. Within 1 to 3 seasons of each reintroduction, the populations had collapsed back to zero. Not poached out, not disease-killed, at least not primarily. Simply unable to sustain themselves in a system that looked, on the surface, like it should work, but functionally did not. By 2010, the cumulative investment in restoration efforts since 1975 had reached a figure that the project's own internal review described as substantial without proportionate ecological return. You'd think someone would have said something. Nobody did. Or rather, people said things. But the institutional response was to fund another round of the same interventions that had already failed, on the reasoning that the problem was one of scale and persistence rather than approach. The dissolved oxygen levels, which had been the primary metric of river health since the Dead Declaration, had by 2015 improved to an average of around 4 milligrams per litre across the monitored stretches. That is real. That is not nothing. 4 milligrams is the threshold at which some fish species can survive in the short term. But fish recolonisation attempts continued to fail, and the invertebrate community, while more diverse than it had been in the 1960s, remained dominated by pollution-tolerant generalists rather than the sensitive specialist species that indicate a genuinely functioning system. And that wasn't even the part that got people angry. The part that got people angry was the modelling. Because when researchers began running predictive models in the late 20-teens on what the river should look like, given the water quality improvements that had been achieved, the model said it should be recovering. The chemistry was approaching viable. The temperature regime was within range. The model said fish should be recolonising naturally by now. And they weren't. That gap between what the chemistry predicted and what the biology was actually doing is where the real diagnosis finally began. A hydrologist named Volkov, brought in as part of a 2019 independent review, spent several months walking the catchment before he wrote a single line of analysis. What he found, or rather what he found missing, was structure. The river had no hydrological memory. The floodplain, stripped of its wetlands and its beaver ponds, could not hold water between rainfall events. Every storm pulse moved through the system fast and hard, scouring the substrate, resetting whatever fragile ecological progress had accumulated. The river was chemically improving but physically broken. Clean water running through a damaged landscape does not produce a functioning ecosystem. It produces clean water running through a damaged landscape. Volkov's diagnosis, when it came, was precise and blunt. "We were treating symptoms," he wrote. "The river had lost its architects." What he meant was that a river system is not a pipe that either has clean water in it or doesn't. It is a structure, a physical, biological, hydrological structure, and that structure requires active maintenance by the organisms that evolved to maintain it. Remove those organisms and the structure degrades. Restore the water quality without restoring the organisms, and you have removed the poison but left the patient without the capacity to heal. The architects Volkov was referring to were not a metaphor either. They were a species, a specific, reintroducible, well-studied species that had been absent from this valley for the better part of 70 years. The restoration program had roughly 2 years of remaining political and financial support before the funding bodies would formally close the file and redirect resources elsewhere. And the clock had already started. To understand why the scientists kept coming back to the same answer, you have to go back much further than the 1970s. You have to go back to a time when this valley, and almost every valley like it across the continent, was a completely different kind of place. Eurasian beavers, castor fibre, were once native across Europe and deep into Asia. Not rare, not occasional, everywhere. In the lowland river systems, in the upland tributaries, in the reed margins and the willow scrub, they were as fundamental to the landscape as the rivers themselves. And then, over the course of roughly 4 centuries, they were almost entirely removed. By the 18th century, hunting pressure for fur and for castoreum, the musky secretion used in perfumes and medicines, had reduced a population that once numbered in the tens of millions to somewhere between 1,000 and 2,000 animals clinging on in a handful of isolated pockets across the continent. Most people never heard about this part. The extinction of the beaver from European river systems wasn't a dramatic event. It was a slow erasure, valley by valley, generation by generation, until the animal simply wasn't there anymore and people forgot it ever had been. What was lost with it was something ecologists wouldn't fully understand until much later. Pay attention to this next detail because it explains everything. A keystone species is defined as a species whose impact on its ecosystem is disproportionately large relative to its biomass. The term comes from the central stone in an arch. Remove it and the structure doesn't weaken. It collapses. The beaver is perhaps the clearest example of a keystone species that exists, not because it is the largest animal in its habitat, or the most numerous, or the most visually dramatic, but because of what it builds. A single beaver dam is not just an obstacle in a stream. It is a hydrological event. When a beaver fells a tree and begins dragging material across a watercourse, it initiates a chain of physical changes that ripple outward for hundreds of metres in every direction. The dam raises the local water table. Water that would have moved quickly downstream now spreads laterally into the surrounding soil. The flow velocity drops. Sediment that was being carried suspended in the current begins to settle. The stream bed deepens and stabilizes, and the water itself, held in the pool behind the dam, begins a process of filtration and oxygen exchange that a degraded, fast-moving river simply cannot perform. Dr. Ivanova had been running hydrological models on the valley for the better part of 18 months when the team began to formalize their proposal. Her data was striking. The dissolved oxygen readings in the target stretch of river were sitting at approximately 2 milligrams per litre. For context, most fish species require at least 5 to survive, and healthy river systems typically sit above 7. What her models predicted was this. Sustained dam activity across the target reach could raise dissolved oxygen concentrations from that near-dead baseline to above 7 milligrams per litre within 2 years. Not decades. 2 years. The mechanism wasn't magic. It was physics. Slower water, more surface area, more contact time with the atmosphere, more biological activity in the margins, creating the conditions for aerobic decomposition, rather than the anaerobic processes that were currently dominating the riverbed. But the oxygen figures were only the beginning. Because once you raise the oxygen, something else starts to happen. And this is where the science becomes, if you let it, genuinely extraordinary. Ecologists call it a trophic cascade. The principle is straightforward enough. One species changes its environment. That changed environment creates conditions for a second species. The second species attracts a third. And so on up through the food web until the effects of one animal's behaviour are visible in the behaviour of creatures that never interact with it directly. In the case of beavers, the sequence is well documented. The dams create wetland margins. Wetland margins are colonised by invertebrates, the mayflies and stoneflies and water beetles that need shallow, oxygenated, vegetated water to complete their life cycles. Invertebrate populations attract fish, which need both the oxygen and the food source. Fish populations attract wading birds, otters, kingfishers, herons. The widened, slower watercourse supports riparian vegetation that stabilises banks and provides cover. Mammals return. The whole chain, unlocked by one species that was absent for 70 years, begins to reassemble itself, which, looking back, was either incredibly brave or incredibly stupid. The idea that you could reverse half a century of ecological collapse by releasing a small number of large rodents and then largely stepping back. The scientific literature supported it. The European reintroduction data was compelling. But the valley in question wasn't a controlled environment. It was a working landscape with downstream landowners, drainage infrastructure, and a public that had been told for decades that the river was beyond saving. There was one scientist who saw all of this clearly long before the X-Force team filed their first permit application. A hydrologist working in a different country, studying a different river system, had published a paper in 2009 outlining exactly the conditions under which beaver reintroduction would and would not succeed in degraded lowland rivers. The thresholds he described for water chemistry, for channel geometry, for the minimum viable release population mapped almost precisely onto the valley. He had argued, in terms that were direct enough to make his reviewers uncomfortable, that waiting for water quality to improve before introducing beavers was exactly backwards. The beavers were the mechanism of improvement. You didn't restore the habitat and then add the animal. You added the animal and let it restore the habitat. Nobody listened. The paper was cited twice in the decade after publication, both times in footnotes. The X-Force team came together formally in 2022. Volkov leading on ecology, Ivanova on hydrology, and alongside them a legal specialist, a community liaison officer, and 2 wildlife capture specialists who had worked on reintroduction programs in Scandinavia and the UK. The proposal they assembled wasn't a simple application. It was a case built across 3 regulatory bodies, 2 years of environmental impact submissions, and multiple rounds of public consultation. The opposition was real. Downstream farmers raised flood risk concerns. Local drainage authorities flagged potential interference with existing infrastructure. And there was a broader public scepticism that was harder to quantify, but no less present. A feeling that this was an experiment being conducted on a landscape that had already suffered enough. Volkov's response to the flood risk argument was methodical. He pulled reintroduction data from Bavaria, from Scandinavia, from the UK programs that had been running long enough to generate meaningful outcomes. In roughly 80% of cases, beaver activity had produced a net reduction in downstream flood peaks, not an increase. The dams attenuated flow. They spread water across floodplains during high rainfall events rather than concentrating it in the channel. The counterintuitive truth was that the presence of beavers made the river more manageable, not less. Final approval came in late 2023. It was conditional. Phased release, continuous monitoring, explicit damage thresholds, and removal protocols if those thresholds were exceeded. The team accepted every condition without hesitation. Standing at the edge of the valley now, looking at the water moving through it, it is difficult to hold in your mind what this place looked like the morning those first animals were carried to the bank. The image from the cold open, that single beaver pausing at the water's edge before sliding in, carries more weight the longer you sit with it. Because that animal wasn't the solution. It was the question being asked of the river. Could it still remember what it was supposed to be? We didn't restore the valley. We returned the animal that knew how and then got out of its way. They said the river was dead. 200 beavers disagreed. Subscribe to catch the next